In this video, I'm going to be talking about Lewis dot structures and how we use them to show covalent bonds. Let's start with a few words of review. Remember that when atoms or elements go together to form compounds, they do it in a way so that each atom has access to 8 valence electrons, and we call that the octet rule. In ionic bonds, electrons move. Metals give up their valence electrons, whereas nonmetals accept more valence electrons. So we end up with ions that have a positive or a negative charge. And in an ionic compound, then, these positive and negative charges attract, and the compound is held together by electromagnetic force. Covalent bonds are found in covalent compounds where you have a nonmetal bonding with at least one other nonmetal. And unlike ionic bonds where the electrons are moving, in covalent bonds, electrons are actually being shared between atoms, and that sharing of the electrons is what forms the covalent bond. But just like with ionic compounds, a covalent bond allows each atom to have access to 8 valence electrons, so the octet rule still applies. Now, there is one exception to this. Hydrogen, like helium, is stable with only 2 valence electrons, so it will make a bond to give it 2 valence electrons, not 8. Each covalent bond then is formed by 2 electrons, one coming from the first atom and the other electron coming from the second atom. So in our illustration here, we have water on the left, and you can see this combination of 2 electrons here. One is yellow to indicate it came from oxygen, and one is blue that it came from hydrogen. That's your covalent bond, 2 electrons, one from each of the 2 atoms involved in the bond. These shared electrons that form the bond are known as shared pairs or bonding pairs, but you also will have lone pairs of electrons that just belong to one atom. They are not involved in any covalent bond. On oxygen, we have 2 lone pairs, and over here on nitrogen, our illustration showing us ammonia, NH3, we have 1 lone pair. Also in covalent molecules, not only single bonds, which we have illustrated on this page, but also double bonds where 4 electrons are shared, or triple bonds where 6 electrons are shared are possible. The chemical formula for covalent compounds do represent just one single molecule. Unlike ionic compounds, where you will have a crystal lattice forming, and we use the simplest form as the formula, the empirical formula, the formula in covalent compounds is actually the formula for the molecule. So phosphorus trichloride is only 1 phosphorus and 3 chlorides. Covalent compounds are sort of opposite to ionic compounds. They have low boiling and melting points, which means they tend to be liquid or gas at room temperature. As a solid, they are soft or brittle, and since they do not have ions, they will not conduct electricity when dissolved in an aqueous solution. So how do we use these Lewis dot structures to show the bonds in a covalent compound? Well, the first step is to evaluate the valence electrons that are present already on the atoms involved in your compound and determine how many more electrons are needed to create that octet. From that point, you figure out what's going to be your central atom that you're going to be building off of. Usually it's the one that has the most bonds needed, and then arrange the other atoms around it. Sometimes it takes a couple tries to figure out how to best arrange things. You want to match your single electrons to make bonds, and we typically draw the bonds in as a line when we're doing a drawing of the finished molecule. You want to make sure you add any lone pair electrons. You show them just as dots around the appropriate atom. And if you are left with electrons that are not paired, then look for ways to make a double or triple bond, because every single atom, remember, has to have access to 8 electrons in order to form a stable compound. So let's do some practice examples. Our first one is water, very familiar to us. So we have hydrogen, which is listed over here in group 1. So it needs 1 valence electron because it has 1 and its maximum of 2. And oxygen has 6 valence electrons, so it needs 2 more to make 8. So of course we've got 2 hydrogen available each to contribute 1 electron to the oxygen to make everybody access to the proper number. So if you think about your Lewis dot structure, oxygen is coming with 6 electrons. So we have 2 places here where the electrons are available to make a bond. And so our hydrogen can supply its 1 electron for each one of these kind of empty spaces on the oxygen. Now we could end our Lewis dot structure here, but typically these bonds are erased, and instead we just draw a line in to show that it is a finished bond. How about NH3? So nitrogen is over here right next to oxygen, so it's only going to have 5 valence electrons. It's going to need 3 more, and again, hydrogen, we know each one has 1 electron and is looking for another electron to be stable. So nitrogen is going to be our central atom, and we'll show our 5 electrons around it. And again, hydrogen is going to match up in each of these, with each of these single electrons on nitrogen, so that we have a shared electrons between the nitrogen and hydrogen in 3 places. And again, if you want to make this neat and tidy, we'll turn these pairs into nice lines for the final product. And then finally we have CH4. And so carbon is right next to nitrogen. We're just going right across the periodic table here. And it has only 4 electrons, so it is looking for 4 more electrons, which will be provided by each one of those hydrogens. So carbon's going to be our central atom. There'll be 4 electrons around, and then we'll have a hydrogen. And I'm just going to draw the dots kind of this way for right now to make my bond lines a little bit easier. So there we have our pairs, and then we can just kind of cover those over and say we're making bonds out of those 2 electrons, 1 from carbon, 1 from hydrogen. And there's your Lewis dot structure for methane, or CH4. Now, as I said earlier, covalent compounds can have double bonds or even triple bonds. So what's that going to look like if you're drawing a Lewis structure? Let's think about carbon dioxide. Carbon has 4 valence electrons, so it's looking to make 4 bonds. Oxygen has 6 valence electrons, so it's looking to make 2 bonds. And of course, we've got 2 oxygen available to bond with the carbon. So if we think about our carbon, just start off, drawing our Lewis dot structures. We've got carbon and we've got oxygen. And remember, you can arrange the dots around the atom when you're drawing a Lewis dot structure, really in any order. You don't have to start at the top. And it becomes very strategic in how you arrange your electron patterns when you're thinking about how am I going to make bonds for these covalent molecules. It might take some erasing and redoing. But if you look at how I have it set up here, it's very clear to see we've got 1 bond that's going to happen right here between the carbon and oxygen, and 1 over on this side. But we still have these leftover electrons that have not bonded. And those are the ones that are going to be available to form a double bond. So there's also going to be a bond here between carbon and the oxygen on the right. And then if we look on the other side, you can see I already made a mistake. So this is perfect. I'm going to have to do a little rearranging of that electron because I really want to make the bond up here. So using the eraser on your pencil can be very helpful. Now this is a very messy drawing, so you want to redraw this in a more neat and tidy fashion, showing the bonds as lines. So we have a double bond between carbon and the oxygen on one side. We've got these lone pairs of oxygen on the other end. And then again, the oxygen on the other side, double bond and lone pairs. So if you look at any one atom, they're going to have access to 8 electrons. So if we just think about the carbon here, it's going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons available to it. And then the oxygen, of course, has the 4 electrons in the lone pairs and the 4 electrons present in the double bond with carbon. So each atom has the octet of valence electrons. This is a stable molecule. How about C2H4? What would that structure be? So again, we have carbon with 4 bonds having 4 valence electrons, and then hydrogen only wanting 1 more to make its 2 valence electrons. So let's start with our 2 carbons and put them in the center and see what we can think of. So we've got our carbons with their 4 valence electrons, and of course very easily you can see we've got a bond that can form right there. And then we have 4 hydrogens that we need to spread around, and it wouldn't make sense to put 3 hydrogens on one side and only 1 on the other. So let's just put 1 hydrogen on, or 2 hydrogens on each side. So we'll put a hydrogen here, and a hydrogen here, and another hydrogen over here, and then our 4th hydrogen. Now we've used up everybody, but we have some unbonded single electrons still sitting up here, 1 on one carbon and 1 on the other. So this is going to form another double bond. So this allows the carbons to have access to 8 electrons. We've got 1, 2, 3, 4, 5, 6, 7, and 8. This one would be the other double bond, and the same on the other carbon. And then to rewrite that, we'll show our carbon with a double bond in the center between the 2 carbon molecules, and then hydrogens off those carbons. There are no lone pair electrons in this molecule, and so you don't show any lone pair electrons. All of the electrons are shown hidden in a bond, shown as a straight line. And then finally, how about triple bonds? Well, nitrogen, remember, is having 5 valence electrons, so it's looking to make 3 bonds, and our nitrogen gas in the atmosphere comes as N2. So we have a nitrogen with its 5 valence electrons, and another nitrogen with its 5 valence electrons. And so again, I oriented it this way on purpose to just make it clearer, to show that we're going to have a bond forming here between these 2 electrons, a bond here between these 2 electrons, and another bond here between those 2 electrons. So in a bond, 1 electron comes from one of the atoms and the other will come from the other atom. So then to nicely rewrite this, we'll show that as triple bonds, 3 lines in between our 2 nitrogens, and don't forget those lone pair electrons. And then finally, another carbon hydrogen molecule, C2H2. So we had C2H4 on the other side, so maybe you can already figure out what's going to happen here. We have our carbon with its 4 valence electrons, our other carbon with its 4 valence electrons. We know we're going to have this bond here joining our 2 carbons. We're going to put our hydrogen, 1 on each side. So a hydrogen off this side and a hydrogen off this side. Those will also make bonds. And then the remaining single electrons, 1 from each carbon, will form the other bonds to make this a triple bonded molecule, 3 bonds between the 2 carbons and just a hydrogen off on either side. And I just want to end with a few words about bond strength. Whenever there's a chemical reaction, chemical bonds are being broken and then they're being reformed because atoms are rearranging as you move from reactants to products. And the stronger a bond is between any 2 atoms, the more energy it's going to take to break that bond. Covalent bonds are generally stronger than ionic bonds. The exact amount of energy will vary. This gets a little bit complicated. And the more bonds you have holding 2 atoms together, so a double or triple covalent bond, will be stronger than a single covalent bond. So this finishes the overview of how to use Lewis dot structures to draw covalent bonds and really to figure out how covalent molecules are put together. It is more complicated than the ionic compounds, but I think after you've had some time to do some worksheets and to practice and be willing to erase and to redraw things if you don't have those valence electrons in quite the right orientation, but after some practice, I think you'll be able to figure it out.